Okay, so yes, recording has started. So this content is now being recorded. So welcome back to the online edition of the operating system class, and let's get started. So first of all, we have a devotional and presentation of the Haiku OS from Jessica. So go ahead and do what you need to do to present, Jessica.
Okay, let me just share my PowerPoint thing, see if I can do the actual. Okay, is everyone seeing that?
Yes, I can see it.
Okay. So, okay. So let's get started. So, yeah, as you can see, my presentation is on the Haiku operating system. I really wanted to make a haiku about this, but I decided against it since. Okay. Let me get on this. Okay. Okay. This is a daily devotion. It caught my eye when I first made the PowerPoint, and I think it really spoke to me. Then the word of the Lord came to me, saying, O house of Israel, cannot I do with you as this potter, saith the Lord? Behold, as the clay is in the potter's hand, so are ye in mine hand. Sorry for the old tongue. I forget what version I did for this. Okay, as clay is in the potter's hand, so are ye in mine hand. O house of Israel, at what instance I shall speak concerning a nation and concerning a kingdom, to pluck up and to pull down, and to destroy it. If that nation, against whom I have pronounced, turn from their evil, I will repent of the evil that I thought to do unto them. And at what instant I shall speak concerning a nation and concerning a kingdom, to build and to plant it. If it doth evil in my sight, that it not obey my voice, then I will repent of the good, wherewith if I said I would benefit them. Okay, does anyone have anything to say about this devotion today? Okay, I'll assume that's a no. Okay, okay, so this is pretty much the history of the Haiku operating system. It started as a Open BOS in 2001. It was from what I remember from my research, the people who worked on it actually worked on the original BOS. But yeah, as you can see, it was taken down after the company was sold, after Microsoft threatened to revoke the Windows license, which honestly, I really wish they didn't do any of that, because it just makes a pseudo monopoly on this. Where, well, not quite a monopoly, but you get the point. Yeah, and most of the code is home built, but there is some code from the original BOS that had been open sourced. And yeah, and you can see those other dates right there. Okay, so yeah, here's some of the properties of Haiku OS. It's open source. It's not a Linux, which may turn off some who prefer Linux, but it also has a custom kernel. So, and has a database-like file system and and an object-oriented API. So if you're interested in that stuff, well, Haiku has all of that. And apologies for the picture. I didn't realize it was Rick Astley. Yeah, it's updated fairly frequently. He has news for new updates and activity that goes on from the official website. There's a free user's guide online and built-in browsers. And unlike some operating systems that we've seen, it does do Wi-Fi and Ethernet. And that's pretty much it.
Okay, are there any questions for Jessica? So it is interesting that that the file system is database oriented, which is a scheme that has been used in multiple operating systems like Multics and things like that. So that's an interesting approach they've taken. And the fact that it's an object-oriented API is fairly unique. So Ethan has a question. He says, what makes it unique in your mind?
Well, aside from what I already stated, I can't exactly remember. It's been a while since I researched it. But yeah, like you said, the database file system is pretty unique among well, not many operating systems do it nowadays.
But yes, it could be a very powerful technique to have database type search capabilities and other functionality within the file system would be useful. Any other questions? So Daniel Jones stated that it's interesting that it's not a Unix variant, yet not Windows makes it pretty unique in his opinion too.
Yeah, and like I said, the original BOS that kind of inspired this operating system was taken down after Windows threatened the company. So
yeah. So I have seen that in the past. I was working with a product that was developed by Intel, which was using or taking advantage of the DSP chip on the Intel CPUs, and it was basically to add capability to create a demand for their DSP or add functionality to DSP. And so we were using it for our real-time operating system to make for our real-time application to make Windows real-time by using this particular library that Intel Architecture Labs had created. And basically Microsoft killed that process. And I don't know if how many of you remember, but there was an antitrust litigation against Microsoft claiming that they were doing monopolistic practices. And in fact, Microsoft lost it. And that was actually one of the key factors that were involved in Microsoft losing the case was their squashing of the Intel Architecture Labs work on using the DSP chip. So I actually firsthand saw the consequences of Microsoft's territorial behaviors in that our project had to scramble for some other solution because it was killed by Microsoft. So yeah, it is unique how that's not just the technical issues, but a lot of the business and political and ethics issues involved. Okay, so I'm going to go ahead and take over unless anyone else has any other questions or comments. All right. Well, thank you, Jessica.
You're welcome.
I'm looking for my applause emoji. Whenever you're looking for it, you can't find it. There it is. Okay, so moving forward, the next one will be Ian Myers will be presenting next on the SUSE, or whatever way you want to pronounce it, operating system. And then after that, we have the history of Unix with Daniel Jones, Hoo-Sin Kim, which I'm not sure if he will be online because he went back, I think, to Korea, but he went back to his home country and has connectivity issues. And Darshini Mohan is also part of that group. And that's the history of Unix. Administrative items are pretty much like I presented last time. I pretty much laid out most of the semester except for not necessarily all the quizzes. But Chapter 5 programming project is due Monday. And then on Wednesday the 8th, we have the Chapter 5 process synchronization quiz. Wednesday, April 15th is the quiz on Chapter 6 CPU scheduling. And again, all these assignments and quizzes you can turn in anytime before the deadline, in particular also the quizzes. So if you want to take the quiz early, closer to when the material is presented, that's certainly an option for you now. And then Monday, April 27th is Chapter 10, Mass Storage Programming Problem. Monday, May 4th, which is, I believe, the Monday before or during the first Monday during finals, the Chapter 12 programming exercise is available for 10 extra credit points. So that's an optional assignment. It is extra credit. And then we will move on back to our coverage of main memory. And the other thing is, for those of you who unfortunately had their midterms lost that took it on paper, please retake it online at your convenience. They are all the same questions, so hopefully you haven't forgotten what the answers were that you had given, and we'll let you take it again. Unfortunately, you had to take it again because those midterms were misplaced somehow over the spring break. Okay, I'm in the process of sharing my presentation. You should see the presentation now, which has the title paging. Let's go back and look where we were. So we're talking about segmentation. Here's a picture of the segmentation hardware. And remember that the segmentation consisted of a segment name, which for implementation purposes usually gets mapped to a segment number, and then an offset within that segment. So each of the segments represent a programming concept like the stack and the heap and other concepts that we use in the actual programming realm. So it's trying to match the way that the memory mapping happens in the MMU to how we actually use it as programmers, how we actually use the memory as programmers. So moving on, we have the concept of paging. So one of the things that paging does is it uses fixed sized frames in the physical memory. They're called frames. And we take the address and we allow the memory now to be non-contiguous. So our blocks can be scattered throughout memory, and the MMU needs to handle, and the mapping process has to handle the fact that our blocks or chunks of memory are not allocated in a contiguous fashion. One of the advantages is it avoids external fragmentation. It doesn't completely eliminate it, but it certainly limits it. So really, the big issue here we have is internal fragmentation. So if we have a fixed size frame, we use a certain number of frames in the physical memory. If we only use a partial frame, that is internal space that is wasted. But we still, these chunks will use all of it. So we have fixed size holes for usage. So we don't have as much of the external fragmentation. In fact, we don't have the external fragmentation per se. It's only internal fragmentation that we have. So, and the size is a power of 2, as between 512 bytes and 16 megabytes are typical paging sizes. And in terms of the way the programmer uses it and the operating system, in terms of the software side, they are referred to as pages. And pages are analogous or one-to-one mapping to the frames. And so on the software side, we refer to them as pages, and hence the term paging. So basically what the MMU needs to do is keep track of all the free frames and then take them off the free frame list as they're being used by a process. To run a program of size n pages, we need to first find n free frames to load the program. That we will see in the virtual memory section that's not necessarily the only, or as far as we can go, but if we were going to load n pages, we need to find n free frames. We set up a page table to translate the logical to the physical address just like before, but now it's a little bit more complicated because we don't have one base register and offset, nor a limit that we can use for managing the memory. And the backing store, which is the storage on the hard disk for context switches, is also split into pages. And again, as we mentioned, you still have the issue of internal fragmentation. So the address translation scheme is generated by the CPU. The pages are divided into the page number and the offset. So we have which page number in our logical memory space, and then the offset within that, and that determines where the physical memory address is the page number and the page offset. So for a given logical address space, 2 to the m and page size 2 to the n is how it will be laid out above. You can see that the page number is m through n, and then the page offset is n. Question? There was a question, I think I heard, or was that? Did someone not mute it? Okay, so again, this diagram here with the page number and page offset is the actual address space of the word of the address. And so it's divided up into the page section and the offset section, and m-n bits are used for the page number, and n is used for the page offset. So again, the page offset n corresponds to the 2 to the nth page size, and then the total logical address space is 2 to the m. So the page is represented by the m-n bits at the top. So here's how the paging hardware looks. You can see there where we have the page and the offset D, and then that maps to the physical address, which is the frame and the offset. Now notice that we now have a table, because you have to have a table of all the page offsets in memory, the page locations in memory. So we now have a page table that keeps track of all the different pages in memory. So that is one extra level of indirection, but it gives us the extra flexibility of being able to work with pages that are non-contiguous for a given process. And that's through the page table. And of course, there's paging hardware that supports that, which is what we're looking at here. So the paging model of logical and physical memory can be depicted here. We have the logical memory, which has page 0, 1, 2, and 3, and our page table that corresponds to each of those pages that has 0, 1, 2, and 3. And then within the page table, we can see 1, 4, 3, and 7, and those correspond to the different processes that are using them. So it would be process 1, 4, 3, and 7, and then we can, or no, wait a minute. No, this is the mapping, sorry. This is not processes, this is the mapping to the physical frames. So we have page table 0, 1, 2, 3 in the logical memory of the process of this. So this is for a single process. I'm sorry, I got off there. And so we see that page 0 of the process's logical memory corresponds to frame 0 in physical space. That page 1 in the logical space of the process is now page 4, and that we have page 3 in the third frame, and then that we have the logical page 3 in the 7th frame of physical memory, and see how they're all scattered about. If we were using the old scheme where we didn't have paging, all 0, 1, 2, 3 would all have to be in contiguous order next to each other. But now we can choose pages or blocks in any random order on the disk, which again prevents the external fragmentation problem, but we still have internal fragmentation when we're not using a full page. So paging characteristics, that's a whole list of characteristics. We have the page size. We have 2K, the process size, et cetera, et cetera. The internal fragmentation would be 2048 minus 1086, which is half. And so 962 would be the average internal fragmentation that we'd have. Is that right? Oh no. Average is the third bullet down from where I was at. On average, fragmentation is half the frame size. The internal fragmentation of this example above is 962 bytes. And the worst case fragmentation would be a whole frame minus 1 byte, right? That would be the worst case. Because if it was a whole frame, that means that frame would not even be used. So we're only using 1 byte in that frame. That would be the worst case internal fragmentation. So one of the questions is so a small frame size desirable, which would be to reduce the internal fragmentation. The downside is that your page size grows, and you have to keep track of more and more pages. So there's a point where that becomes counterproductive in terms of the management and tracking of the page table. So Solaris page sizes have been growing over time as we have available to us larger and larger amounts of memory. So for Solaris, their 2 page sizes were 8 kilobytes and then eventually 4 megabytes. The process view and the physical memory are now very different in terms of that the mapping is very different, because the ordering and the fact that they're not contiguous means that there's now a greater discrepancy between the physical memory and the logical process view of the memory. And then by implementation, the process can only access its own memory. Again, there's needs to be protections in place so that it can only access its own memory. The page table is kept in main memory for efficiency because you don't want to have to page out in and out the page table. And the page table base register points to the page table, and the page table length register is the limit, so you know the bounds of where the page table is located. And then in this scheme, every data instruction requires 2 memory access, because now you have to access the page table, which then takes you to the physical memory, which contains the data or the instruction. So it is now a 2 memory access, and it is indirection. There is an indirection. There's a pointer. There's a table pointer to a table, which then points to the memory. So there's an indirection involved. The 2 memory access problem can be solved by the use of a special fast lookup hardware cache called associative memory, or translation look-aside buffers. So that's the way we can optimize it. Is we know that the page lookup table is going to be critical because everything is going to go through it. So we can use special memory that is faster, and then for the associative memory, that means that there's quicker lookup capabilities, that you can search that memory for the right page table quicker. So these are 2 hardware mechanisms that can be used to optimize this paging algorithm. So page table implementation. So we had the translation look-aside buffer, TLBs. So the TLBs store address space identifiers at ASIDs. And we're going to acronym soup here. In each TLB entry, uniquely identifies each process to provide address space protections of that process. So again, in that table, you will have the process identified so that we can check whether this access is in fact by the owner of this page. And then this is important because otherwise we'd need to flush at every context switch. If the page table contained only the pages for the process that is currently running in the CPU, you would have to do a context switch of the lookup buffer. So we instead use the unique identifier identifying which process is associated with. TLBs are typically small, 64 to 1024 entries. And on a TLB miss, which basically you can't find it, that there are replacement policies must be considered. And so some entries can be wired down for permanent fast access, which basically says this is an area that we're going to access frequently. For instance, maybe a special kernel process. We would say that this cannot be swapped in and out of the TLB because, again, the TLB has a fixed size with a hardware support. So it would have to be brought in from conventional memory if it's not in the TLB, if we exceed the size of the TLB. So any questions about what we've discussed so far on paging? I'm realizing we're going really quick, and I'd like to slow down a little bit and make sure that we're not missing any questions. So it's a common concept, and paging is dominant in current modern operating systems. So yeah, you would be hard pressed to find an operating system that isn't using some form of paging. That would be very unusual. Okay. So we talked about associative memory, which is a parallel search, which you can actually address the memory based on the page number. So you can search for a page number directly as a way to address the memory by page number, and then you would get returned the frame number. So the address translation from page and offset, the association would get the frame out automatically, and then you would then from the frame get the offset from the page table location in the frame. So again, it's like hardware database search support, and we do see associative memory used in database type applications as well. So it's the ability to address the memory by the contents rather than just by the conventional addressing scheme. So here's what the paging hard would look like with the TLB for the MMU. We have the P and D logical address space. We go to the TLB. If there's a hit, then we just take the frame and the offset that goes to physical address. If there's a miss, then the page table information for the page would have to be swapped in from the page table in memory. So that page table there represents the in-memory page table, the whole table, and then it would be loaded in, and then you would get the frame and offset and the mapping to the physical address. Memory protection is implemented by associating protection bit with each frame to indicate if it's read-only or write access allowed, and it can also be more bits to indicate the page execution and so on. So this is done with a valid invalid bit attached to each entry in the page. So you can see that the main point here is that there's various housekeeping besides the mapping values that are involved in the page table mapping process, and one of them is valid and invalid bits. And so for the memory protection, any violations would result in a trap to the kernel to handle this illegal access to a particular frame in memory or a page in the logical sense. But it's basically saying you can't access that page which corresponds to a frame that is owned by some other process. One thing to keep in mind is it is possible to share memory between processes, and we need a mechanism to share pages. Examples are shared code, one copy of read-only re-entrant code shared across systems. In general, the DLLs that we talked about that are shared would be of that category, and in which case you would not have multiple copies of the same shared DLL, so that you would be fixed and shared, and the pages could access, multiple threads could share that same process space. And it's also useful for inter-process communication, where you've agreed on to share a bunch of memory. If you remember the reader-writer problem and the consumer-producer design pattern, those are all cases where you would be utilizing shared memory. Again, we have the process synchronization mechanisms in place to help us handle that, and the operating system would allow these processes to do it. But then the processes have to agree upon some synchronization mechanism to then verify that that the processes aren't walking over each other. And then we have private code and data. Each process kept a separate copy of the code and data, and it's private, and other processes are not allowed. So that's sort of a contrast to the shared code and data. So the structure of the page table is as follows. We can see here, you can read those bullet points, but it's basically running through an example. Consider a 32-bit logical address space as most modern computers. Now we have 64-bit address spaces, so you can see as time moves on, things get bigger. Page size of 4 kilobytes, which is 2 to the 12th, and that means the page table would have 1 million entries. 2 to the 32nd divided by 2 to the 12th would be roughly 1 million entries. So if each entry is 4 bytes, 4 megabytes of physical address space, divided by memory for page table alone, this amount of memory costs us a lot. We now have a problem in that we're using a considerable amount of memory for the page table itself. And so let's say we don't want to allocate that much memory contiguously in the main memory. 3 schemes have been created to handle this situation where the address pages and the physical memory has gotten large enough that now our page table has gotten extremely large. There's hierarchical paging is one of the techniques, hash page tables, and that you'll see is good for sparse data usage, and we'll describe what we mean by that. And then we have inverted page tables as another technique to handle this. So we'll go through those. So a hierarchical page table is simply like the name hierarchical implies. Basically, you take your access into a page table, which then takes you to another page table, which eventually gets you down to the memory. So again, you add another layer of indirection, which allows you to span greater regions. And so in a hierarchical technique, you would then use less memory, but the downside is you add extra memory accesses. So a simple technique is a 2-level page table, which is depicted here. And so now we have not only access to a page table, but we have then access to another intermediate page table and then to memory. So again, the downside is the extra dereferencing or the extra layers that we need to go through, levels of indirection. But the advantage is that the page table size becomes reduced, or the memory needs of the page table becomes reduced.
How does that work? As in, like, does it group the like memory that is all that like needs to be contiguous like together, and then I'm just kind of confused on why you would want to.
Yes, good question. So it's not, so in paging you get kind of avoid the term contiguous because they aren't necessarily contiguous, but yes, the outer page table points to the memory address and offset into the next page table. So we can see here that we have 1.500, 100.708, and 929.900. These are all different page tables that have random pages, page frames in them, and logical pages. And the first arrow points to a table in the next page table. So you're actually pointing to a table, not to a physical address.
Okay, that's interesting.
Yeah, it takes a while to get your mind around. So you're actually pointing to another table, and then from there you're searching that other table.
So in the first so like let's start from the outer page. The outer page goes to like the first part of the first frame. Is that like the frame of that page table in the middle?
Yes. So let's take the outer table. We had that first block in the outer table, and that points to that first block or array lookup table. So we know we then go from the outer table pointer to the table that says, okay, this is a table we need to look at. And then we look in this space, and that then maps us to the physical memory. So you ask us, well, wait a minute. So we're pointing to this table, and all the pages or frames that are in use are in there. So how does this save us memory? Is that kind of where you're going with this? Or am I putting words in your...
Well, I'm just kind of wondering, like, is it just narrowing it down, like, as it
Yes.
goes? So
Right.
that's how it kind of works,
Yes.
even though
So,
like it even overlaps.
right. So think of this as a tree search,
Mm-hmm.
right? So we're going, okay, we're going to go down this branch, and then we're going to go down this branch. And if we do multiple layers, here we're only doing 2 layers. So you go left or right, and then from there you span out to that table.
Yeah.
And so if there's not a frame being used, it would not be in that page of page tables, because it wouldn't be in one of those page tables, and you would have a miss.
Mm-hmm.
Yeah.
And if you have a miss, then you're gonna have to like go back to the outer page table and then, or like do it again.
Well, you would actually have to have a new entry entered in, and it would be put into one of the page tables that are in the page table.
Yeah.
Right.
Even though, like, so it could be in another point of memory, but you didn't, like, since you didn't go there, then you have to put it in this one that you're already in.
Yeah.
So, okay.
Yeah.
All right.
So you got levels of indirection that span out, and so that makes, so the primary advantage is what? What are we doing? We're doing a tree search. So think of your data structure class. We have a binary search, and so now we have made the memory searching less. If we were marching through this huge table one by one, it would take us forever to get there. So in essence, we're doing a tree search for the mapping rather than linearly going down the whole page table as a linear page table. Does that make sense, or does that clarify, or does that make it more confusing?
Yeah. And
So
I
think of this as a tree. When you have a tree,
Yeah.
so that's what you're doing. You're setting this up as a tree. And we also have databases that use that same concept. As you know, we look at various tree structures, in particular binary trees, for accessing and searching through data or sorting data. And so this is a common concept in data structures as well. And so we're just applying this to the implementation of a page table for searching for the mapping.
Yep.
Any other questions?
I think Bailey said, what does the page offset mean again?
Okay, so the page offset is the once you find the frame or page. So the page is the logical term, and then the frame is the physical. So they're kind of interchangeable because they kind of map. It's once you get to the frames, let's say, it's the offset into that page for the specific memory location that you're trying to access. Yes, and so Timothy's saying the last bits of the virtual address are called the offsets, which is the difference between, and I have to do the see more, but I'm thinking you're going to say the base. Yeah, the actual memory address you want, and the start of the page, which is the base for that page. Yes, or frame. Yes, exactly. That's a good way to state it, Timothy. So that's what the offset is. It's from the beginning of that page or frame. Again, you can kind of use those terms interchangeably. One is the logical view and one is the physical view. The frame is the physical view. Okay. So 2-level paging example. I think I probably won't go too much into it. Take a look at it, see if you have any questions. But basically, that's what we just discussed here. You can see your address space is divided up into a reference to the inner page table. P1 is the table, and then P2 is the next table, and then the offset. So really, you're using the address space as a way to implement your hierarchy, your hierarchical search. And so you can segment the memory address into each of the components, the first table, the second table, and the offset into eventually that frame or page that you're trying to access. So again, the offset is the difference from the beginning of that page or frame. So just terminology, that's known as a forward map page table. Any other questions about this slide? Yeah, this is just sort of an example of what we kind of discussed on the first slide. With the additional benefit if you can actually see the address space and how that would be mapped into the hierarchical system. The other solution is a hash page table. So where would a hash page table be useful? I've kind of mentioned that, but going back to your data structure class, what advantages does a hash page table have? Or hash table, sorry, in general, the data structure hash table. And why would we make a hashed page table?
Speed.
Speed, exactly. We narrow it down by some hash algorithm that will then map us into a set of table entries that we want to look at. So again, we have a quicker access. We don't have to search through the whole page table. It's sort of a different way than doing a tree search that we have a hash. What other benefits do we have? So in particular, it's useful for sparse address spaces. So what we mean by sparse is that not all the data values are being used. And we don't want to search for it. We want to quickly know through the hash that we made a miss, that's not available. We don't have to have storage for it. We just go to the hash and say, boom, there's nothing there. It's null. And so we don't necessarily have to have an entry for every page or frame. Again, I'm kind of using that page and frame interchangeably, but remember that the frame is the physical side of things. So the other advantage is that if there isn't a physical frame for it, it won't be in any of the chains. So going forward here, we have the virtual, going through the slide here, we have the virtual page is hashed into a page table. This page table contains a chain of elements, right? So that's what a hash looks like. The hash points you to a chain of elements to check. And each element contains the virtual page number, the value of the map page, and a pointer to the next element. So again, the virtual page number and the value of the map page frame is what we had before. The pointer to the next element is just the less component, where it's the housekeeping for keeping. I got here that my grandson, which is not true. Yes. So, and then page names are compared in this chain, searching for the match. Again, just like you remember seeing in a hash table in your data structure class. And then variation for 64 address spaces is clustered page tables. They're similar to hashes, but they refer to several pages, such as 16 rather than 1. So it's just another housekeeping and efficiency choice is to cluster the pages. And again, repeating what I said earlier, this is especially useful for sparse address spaces where memory references are not contiguous and they're scattered, and we have holes of physical memory address spaces, or we can have holes of addresses that aren't currently being mapped to anywhere. Okay, so that takes us, let's see, 246. It takes us close to the end of the class. Any questions before we say goodbye and sign out. Any questions about, again, the material or the class in general? And again, those of you who unfortunately had their midterm lost, please take the opportunity to go in online and take the midterm again. I'm sorry that happened. The administrator looked all over the place, every conceivable place, and they just have gone missing. All right, well, I'm going to go ahead and stop recording. If you have any other questions that you want to ask me offline,